Hello, my friend. Today we keep going on with the following exercise in the Euler project, which is this one. Even Fibonacci numbers. All right, today we're going to stumble upon recursion, which is this very strange and difficult concept in computer science, I would say. I struggled a lot with the concept of recursion, and today we're going to understand it better. So basically, with this problem, we have to find the sum of the even valued values do not exceed 4 million. Okay, so I have my Fibonacci sequence that starts at 1. If you don't know, the Fibonacci sequence is this sequence indeed by which all the numbers follow a specific pattern. As you can see, we have 2, which is the sum of the previous 2. Then we have 3, which is the sum of the previous 2. As well, 5 is the sum of the previous 2, and so forth, till infinity. This is a sequence which holds the name of Fibonacci, which was this fellow here, which, by the way, was from Pisa, which is fairly close from where I live. So Fibonacci. And behind the Fibonacci sequence, there is all this mystic that surrounds this sequence, because it seems like that nature really likes to be like Fibonacci. There is this concept of the golden ratio, which is almost like 1.6 something. Now I don't remember. 1.6180 and so forth. The golden ratio, Fibonacci. And as you can see, it's tightly linked to the Fibonacci sequence, because as the Fibonacci numbers get bigger, the ratio between each pair of numbers gets closer to the golden ratio. The number is called phi from Greek. It is this symbol. And yeah, you can dig as down as you want with these ideas. All right, let's jump to the code. So as usual, we go in the terminal, I cd into my desktop, and then I cd into my Euler project, which is this directory here. Here you have the terminal, and here you have the GUI representation, but it's the same thing. We programmers, we work inside the terminal. Now, inside this directory, I see that I have only the problem 1, so I'm gonna make dir problem 2, and I'm gonna cd inside problem 2. Okay, now I'm inside that directory. Basically, you see, my friend, I created another directory, and now I cd inside it. So now I'm here inside the terminal here. Cool. So let's start with C. So I'm going to do vim main.c as always. So how do I tackle the problem? To solve the Fibonacci sequence, we are going to exploit recursion. Now I'm going to write the code with you, and then I'm going to try to decipher step by step. First of all, like always, we're going to include our standard input output, of course, to use the printf. Then we're gonna start by the main function. So int main as always, and then we start to reason how to tackle the problem. So I need to sum all the even numbers of the Fibonacci sequence. So I'm gonna need function that is gonna give me back all the Fibonacci numbers, right? First of all, I want to show you how to write a series of Fibonacci numbers, okay, in a naive way. So I'm gonna do int I is equal to 0. This is my iterator. Basically, it is the index of the number in the Fibonacci sequence. And then I simply say while 1. So this is while infinity. This is an infinite loop. What do we do? I say printf, the next fib number is %d. Go on the next line. Here I put my function that now I will define, which is fib in position I. Then I press ask, open, so I go in the next line, and then I increase I. Here I write I in the following line for ease of comprehension, but I could have written ++i directly inside here. Anyway, so this is my main function in a nutshell. That is gonna print all the Fibonacci numbers. Now, of course, I have a warning, because the compiler is telling me implicit declaration of a function fib. All right, where is the function fib? I don't know. Give me the implementation of the function fib. And now I'm gonna make the implementation. So I'm gonna use int as a return value, fib, int and b. I can say index better, small trail. Okay. Then, my friend, I have to use recursion. Now, first of all, I'm gonna write, and then I'm going to explain you. So I say if index is equal to 0. Now, this is the right way to write a Boolean expression, right? Index equal to 0. But I really enjoy this fashion of writing, like 0 equal index. Basically, I invert the number and the symbol, because very often I get this bug, index equal 0, but this is not a equal, right? This is an assignment. And this is an operation that is possible in C. For the compiler, this is okay. Now I have a warning because I have a special plugin in Beam, but for the compiler, this is correct. So to me, personally, I prefer to invert like this index, given that this is the same expression. This is the same Boolean expression. So I say, if the index is 0, namely, if we are here, the index 0 is the first number, what do? You return 1, right? Else if 1 is equal to index, what do? Well, if the index is 1, we return 2, okay? Return 2. Otherwise, given that we have a recursion here, you can switch the word the recursion with the word repetition. And here we have a repetition that is going on toward infinity. Basically, we have every time the sum of the previous two numbers. This is a recursive definition. We return what? The Fibonacci of index -1 plus Fibonacci index -2. So the sum of the previous two numbers, you see. Now let's launch the code, and then I will give you some more explanations. We check if it is correct in the first place. So ZZ, we compile the code as always, gcc main.c, and then we launch it. As you can see, we have our program that is running. I have 1, 2, 3, 5, 8, 13. So it seems like it's working, right? 13 plus 8, is it 21? Of course, 21 plus 13, 34. And it's going on toward infinity. But as you can see, the program is not so fast. It's like slowing down. We have the first numbers that are generated immediately, but as long as the program is running, we have a big slowing of the process. And then, of course, we have here an overflow, right? Because we are using integers. We need data structures which are bigger than integers to all bigger numbers. Anyway, the problem wants all the Fibonacci which are even below 4 million. So here we have 3,524,578. So basically this algorithm is okay. I just need to select all the even numbers which are in this first part of the algorithm. But we are here to learn, and we are here to understand things. So we're going to make an algorithm which is much better than this, even though I'm using a MacOS, Intel MacOS, so I don't have the chip M1, but it's still a good computer. Given all this power, the program is already frozen, basically, because there is a shit ton of calculation that is going on. Okay, let's interrupt this process and let's decompose. Let's understand what is going on. Regarding recursion per se, what is going on here, I made a video which is a doc for recursion, in my opinion. This is a gimmick that I've developed to understand myself what is recursion, because I was really bad. I couldn't really figure out how recursion worked. So I came out with a mental model to understand recursion from a practical standpoint. So now I can write recursion pretty easily, and I would say more, I prefer recursion because basically you can resolve things iteratively with a while loop or for loop, or recursively. It's like a tool in your toolbox. Certain kind of problems are better suited with recursion, while other kind of problems are better suited with iteration. We use the Fibonacci case to use recursion to explain recursion usually, even though I think it's not super easy initially. I recall that I really couldn't understand these lines when I started to code. So I prompt you to watch my video. It is an explain like I'm 5 kind of video. Basically, it was designed for my nephew, which is a kid, and allegedly could write recursion after he saw the video. So it was my unit test. So given that you understand what is going on here, that this is a base case, this is another base case, and this is the recursive call. What we can do to increase the performance of this algorithm? Well, first of all, we have to change the data type that the function is using. I would say the biggest data type available in my toolbox, which is an unsigned long, right? This is the biggest data that I can use in C. Of course, this is so ugly to see, right? Unsigned long. So what we can do? Well, we can include an header file, which is standard int, and this header file contains a lot of good stuff. Just go here in the open group and go to standard int. Basically, inside this file, you have a set of symbols that you can use to write more concise data types. For example, here you have uint 16_t. This is an unsigned integer that is using 16 bits, namely this is a short, right? This is an unsigned short. This is an unsigned int, and so forth. Here I have also the unsigned int 64. So this is a long, the biggest one, unsigned. So this is the biggest I can use. All right, so we write, now I don't know if long is a thing or unsigned long is the biggest. So is long, I guess 16 bytes. So how many bytes? It's unsigned long. It's 64 bits or larger. Is the same as unsigned long int, guaranteed by C to be at least 64. Anyway, so now we use unsigned int 64, right? Unsigned int 64. You see how more concise is the code? Perfect. Then we have to change, of course, the conversion specifier here at the printf. So long digit, right? Save. Seems like everything is correct now. So with this trick, we fixed the overflow problem up to a certain point, of course, but this is a big number already. Then we have to fix the performance of this algorithm. You see, my friend, the problem with the Fibonacci sequence is that we get a series of calculations that have this structure. As you can see, I have Fib7 that is going to be decomposed in Fib6 and Fib5. Fib6 is going to be decomposed in Fib5, Fib4, right? You have a series of decompositions. So you get this tree data structure, which is, of course, a recursive data structure. And every branch of this tree is going to end with the base case, right? We have two base cases here. Now, the problem is that Fib5, for example, or Fib4 is calculated many times, like here, here, and here. You have to calculate many times the same function. When you get, for example, Fib 300, you have a lot of calls that probably have already been made. So the bigger the number, the more calls you have to do. For Fib 300, you have to make a shit ton of calls because every call is gonna branch in subcalls. So here we can use a trick which is called memoization. You see here, memoization. And this is a trick that is very good. Here you can watch Fibonacci and memoization. So basically, as you can see from the picture, the problem is that we have many times the same function with the same value that gets called. But I want this. I want to save Fib4, Fib3, Fib2, Fib1 inside a cache. A cache is a place where you stock results that you have already acquired. So we're going to create a cache. How do we do that? Well, we can use an array, right? We can use an array, which is a piece of memory that is going to act like a cache. Okay, so I'm going to do unsigned int 64. I'm going to call this cache, and this is an array, okay? An array, we say, of 512 elements. Pretty big array. Then here I'm going to initialize the array. This is an initialization. And I put inside the first spot, namely the one in position 0, the value 1, right? And in the spot number 1, the index 1, I'm going to put what? I'm going to put 2, okay? All the other values are going to be initialized to 0. This is the way initializators work. Just search for initialization array. Cool. Then here, what do? I say return, if the index is equal to 0, return cache in position 0, right? Here I say return cache in position 1. And here, what do, my friend? Here I have to change a little bit. So we start with the else block. This time, before calling the recursion cascade of calls, I have to check if the recursion for that specific index has already been made. So I simply say if cache in position index, right? If cache in position index in my array, so namely, is there a value? Is it a value different from 0? Namely, this Boolean expression is going to resolve in true, right? If I have a value different from 0. It's like saying different from 0, right? But this different from 0 is redundant. Nonetheless, let's leave it so it's more readable, maybe. What do? Well, you just return it. You just return it, so cache index, because it means that in a previous call, we have already resolved the riddle. So on the contrary, if the specific index in my array is 0, what does it mean? Well, it means that the function is yet to be calculated. So we have to calculate it now. So I'm going to write cache in position index is equal to fib index minus 1 plus fib index minus 2. Okay, this is the recursive call. So it's going to do all its business. This recursion is going to calculate all its sub functions, and it's going to return inside the cache in that specific index the value. Okay. And what do? I just simply return cache index. All right. Seems like I finished. So basically, the recursion is still the same. If the value is 0, return what is in the cache in position 0 that I already initialized to 1 and 2. Otherwise, return the value in position 1. Else, in the recursive case, first of all, check if there is a value inside that specific index in the cache. This means that I have already calculated that index. If this is the case, return that value. Otherwise, you calculate it, you stock it, and then you return again that value. Let's try to launch this time the program. Okay, it's easy. Compile, launch. As you can see, my friend, there is still a problem. The problem is going, but it is still very slow. What is going on? What is the problem in your opinion? Just stop the video and try to think for yourself. As you can see, it's like before. The only thing we have solved is that I don't get the overflow. The numbers can be pretty big. The algorithm is working. As I can see, I have my fib sequence, but this is a broken algorithm, quote unquote broken. Let's try to understand what is going on. The problem, my friend, is that this cache, every time disappears, quote unquote, is not a real cache. I want that all the times the fib function is called, all the values that are healed stay inside the cache. So I can do in two ways. I can make this variable global, right? I can put outside the function fib. And this is going to become a global variable that everyone can see. But global variables are not a big thing. They're not very cool because they can create a lot of bugs. So we can do something better. We can put inside here static, the word static. First of all, let's launch again the program and let's watch what has changed. So I'm going to compile and launch. Boom. As you can see, my friend, it is like instantaneous. I have a lot of numbers. Now I do like that. I do a.out pipe add, I don't know, 50. I'm going to take only the first 50 numbers. And as you can see, it's almost instantaneous. It's instantaneous, the program. So now, what is the static? What is happening here? When you declare a variable static, you're going to create basically a global variable which is accessible only by the fib function. When I call the first time the function fib, I have this cache that gets created and gets initialized with these values. So I have in position 0, 1, in position 1, I have 2, and all the other values are zeros. Once we get this initialization for the first time, I get this cache that is alive, as long as the program is alive. But the catch is that this variable is accessible only by the fib function. So it's like I have a global variable only for the fib function, which is what I want. So every time I get a specific value for a Fibonacci call, I'm going to stock inside my cache that is always alive, okay? And it never dies. If I remove this static, this is not the case. All right, this is not meant to be a course on the C programming language. So I pledge you to watch what is a static variable from Code Vault, which explains very well what is going on. So this is our very performant algorithm that is giving me back the Fibonacci number at a specific index. Perfect. Now back in the main, I say unsigned int 64. I call it fib NBR. And here, what do? I don't put 1. Then I create a variable counter, still unsigned int 64, which is pretty big. And I call it counter. Tac, perfect. Counter is equal to 0. We have always to initialize a variable, otherwise you're going to get junk value inside. Then inside my while, I need my Boolean expression. And I put fib number is equal to fib in position I, okay? And this is my Boolean expression. So I have an assignment, which is going to resolve in the value of the variable fib number itself. So I can do this and say, I put the braces because this is more readable. So as you can see, I'm going to get this value. And what is the condition? While this value is minor than 4 million, right? 4 million. This is my condition. What do? Well, you put inside the counter plus equal that value, right? Fib number. And then as always, you have to increase I, okay? So the loop keeps going on until we hit the condition by which the Fibonacci number is major than 4 million. Now we have to find the sum of the even Fibonacci numbers, right? And we know pretty well from the previous exercise how to do that. So we're going to do if not fib NBR, what? Modulo 2 in parentheses. Otherwise, the bank is going to have a major precedence. So this is the operation. So basically here there's written, if the number is even in computer language, what do? You increase the counter with that value, and then you increase I so you can have the call for the next Fibonacci value. Okay, it seems we are finishing, and then we call printf. The result of the riddle is %d new line count. Okay, so my friend, it seems like this is the code, right? Do you see any bugs? Yeah, this here I have the format specifier, which is not correct, LLD, and then seems like everything is correct. Okay, ZZ and launch. ZZ main dot out. Okay, the result is this one, 4613732. Copy. Okay, I passed inside this spot check. We're gonna see if it is correct. All right, congratulations, the answer I gave the problem is correct. Cool. We solved the problem with a very efficient algorithm that exploits memoization, even though it wasn't necessary. But anyway, so here, my friend, there is a lot to unpack if you wanna really understand what is going on. Here you have to understand recursion. So I pledge to watch the video I made or find yourselves the best way to understand what is going on. This strange symbol comes from this header file. And of course, you have to understand what is this static, which is pretty useful, as you can see, especially in these cases when I need a cache here. This concept of memoization, it's another key idea. What do we mean by initialization versus assignment, for example? This is an initialization and not an assignment. So I can do stuff like that. Recursion, static memoization, and that's it. These are the new ideas that you have to dig for yourself. All right, let's try to write this code in C++ this time. We're gonna make it fast because it's basically the same. So vim main cpp. My friend, this time I just show you the end result because it's the same basically. The only difference is that I have to include the IO stream. Then the fib is the same, exactly the same code. The only thing that changes is the printf, and the only difference is the other file. So 2 lines are different. Makes no point to write together this code. So I'm just gonna compile and then launch. As you can see, it's just printing all the Fibonacci values till 4 million. Okay, so as you can see, this is correct. Here, indeed, I just print the value. I just don't do the sum, just to make it different. So otherwise, it makes no point. So this is the Fibonacci sequence. You see how fast it goes? I can make it a bigger number. Let's see how it works. So I compile and then I launch. You see, instantaneous. Let's make it even bigger. Here I put 0, 0, 0. Okay, all right, I compile and then run again. Same idea. Thanks to memoization. If I happen to change only one line of this code, which is static, right? Every time the values in the cache are not saved, look what is going to happen. You already know this stuff. A.out, and we go back in slow motion, my friend. Only one word. So you have to understand very well the static is pretty useful. Now we conclude with Python. So main.py. And Python is, as you know, amazing because in few lines we can do everything. But this time I'm gonna use a list. Of course, this is not meant to be a course on Python, so I write like you know the Python language. Okay. So basically, what we're gonna do, we're gonna create a list that I call fib. Fib is equal to I give immediately the values 1 and 2, which are the first 2 values of my list. Then I say while fib in position, in the last position, so -1. Indeed, we can index a list with this special way of doing, right? It's very different from C. In C, I should have written something like that. Fib in position len fib -1, right? This is the C way of indexing the last element. In Python, I can immediately take the last element with no problem. So my condition is while fib -1, the last element, is minor than 4 million. What do? Colon. We append, okay, in my list, what? The value, which is the sum of the previous 2. So fib -1 plus fib -2. You see? Easy peasy. So here we have already our sequence of values, basically. We have already our Fibonacci sequence. We exploit the ease of use of the lists in Python, which are amazing. They are basically like arrays on steroids. They are super useful, super easy to use. I can use different data types inside lists. In arrays, in C, I cannot. They are dynamic arrays, basically. But let's not delve into it. So I'm going to print now the result. But what do I have to do? First of all, I have to filter the even values. So I'm going to use the function filter. The function filter takes as an input a function, which is indeed the filter that we want to use, and an iterable, which is my list fib. So I'm going to use the lambda keyword to create a function on the go that I can use immediately and then throw away. Lambda that takes this input x and gives me back a boolean, which is x modulo 2 is equal to 0. This is my filter that I want to use in my iterable, which is fib. Okay, so the combo filter plus lambda, which is a function created on the go, and the iterable is gonna yield all the values which are even inside my Fibonacci list. Okay, now the problem is that in the last position of my fib, I have a value which is bigger than 4 million, right? So I take a slice of this list, which is till -1 not included. So this operator is like saying, give me the list, but not the last one, not included. This is the slice operator if you want to dig by yourself. Okay, so I have this series of objects. What I want to do with these even values of my sequence? Well, I want to sum all of them, right? So I'm going to call the function sum. Sum, parentheses, and then close parentheses. So basically that's it, my friend, right? I think so. So delete. We're going to launch this code, Python 3 and main.py. 4613732. And as you can see, 4613732, right? Cool. In Python, look how amazing it is. You can collapse a lot of complexity in few lines. Now let's do something. Got main.py. I want to show you a very good way to see this code. This is called Python tutor. By the way, it works also with C and C++ code. So this is pretty dramatic, useful. It allows you to visualize your code so you can really understand what is going on. So let's watch our Python code in action, visualize execution. Next, as you can see, I have my list here. In Python, we have objects. It's kind of different from C. So we have our list objects. Then we do this operation. While fib -1 is minor than 4 million. Append the sum of the previous two, as you can see. So every time we do the sum of the previous two, look here. Boom, 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 boom. We go on and on and on and on. At a certain point, we're going to stumble to a value, as you can see here, which is bigger than 4 million. Cool. So I have my list of 33 elements. Then we go here. We have the lambda, which is represented by this sign. That is going to be filtering all the positive values till fib -1. So the last 5 million is not included. So we filter, or you see, for 1 is false. Then for 2 is true. For 3 false, 5 false, 8 true, and so forth. So the lambda is going to filtering all the positive values. And then the sum, of course, is summing all these values that have been filtered. All right. So here's the end, and then we print our solution. So that's it, my friend, for this video. I hope you enjoyed, and yeah, I hope you learned something new. Enjoy, my friend.